Hello everyone, and in this video we're going to be discussing a very special triangle center and some of its really cool properties, and it's called the orthocenter, which is the intersection of the altitudes. Specifically, we're going to be discussing a concept that's related to the circumcircle itself. So let's go ahead and add in the circumcircle here. So we have ABC, AD, BE, and CF are the altitudes, and H is the orthocenter. In other words, it's the intersection of all the altitudes. So the question that we want to ask is, what happens whenever you reflect H across the side BC? In other words, what happens when you extend this and then you have a point here X such that HD equals DX? So we have these lengths are equal. Let me go ahead and add that. Well, it clearly looks like in our diagram that X seems to lie on our circumcircle. Why would this be the case? One way to try showing this is that if X is a point such that HD equals DX, we want to show that ABXC is cyclic. So how could we do this? We want to try finding some very promising angles with X. So we have that angle XBC. We should try considering that because we also have that we want to prove that it's equal to XAC, and XAC we know it pretty solidly that it's 90 minus C. So we want to prove that angle XBC is equal to 90 degrees minus C. There we go. Well, from our reflection property, we know that this is equal to angle HBC is equal to 90 degrees minus C. So this is what we want to prove now. Well, we know that H lies on BE, so now we want to prove that EBC is equal to 90 degrees minus C. But now you should notice that this angle here is C, this is 90 here, so this is also 90 minus C. So that means that angle XBC is 90 minus C, as is angle XAC, which means that ABXC is cyclic. So now that we know what happens when we reflect H across BC, we now want to see what happens if we just rotate this thing 180 degrees. That is, we have a point M here, which is a midpoint, and we spin this thing around 180 degrees. So let's go ahead and do that. Because whenever we spin something 180 degrees, we get a parallelogram. So let's go ahead and finish the parallelogram. There we go. And we have Y. So now we have that Y also appears to be on the circumcircle, sorry. So how can we go ahead and prove this? We want to somehow use the fact that HBYC is a parallelogram. So how can we go ahead and use the fact that CH and BY are parallel? Well, by definition, we have that CH is perpendicular to AB. So we have that CH is perpendicular to AB. But then CH is parallel to BY. So it should be pretty obvious that BY is perpendicular to AB. Similarly, looking at HB and YC tells us that CY is perpendicular to AC. So we have two 90-degree angles here, and these opposite 90-degree angles add up to 180 degrees. So not only does Y lie on the circumcircle, but even stronger, AY is a diameter. Very strange, right? Go ahead and take a moment to contemplate this really interesting fact. With that in mind, we can actually use the other altitudes. So let me go ahead and extend those. and then those are like, suppose, W and Z. And then we have the midpoints here, N and P, and then we intersect, and then we extend those. And then the reflection of H across N and P also lie on the circumcircle. So let's call these points Q and R. Given all of these like lengths that are like double the other ones, for example, HW is twice HF, HR is twice HP, and so on, it kind of motivates us to take a homothency centered at H of scale 1/2 and see what happens. Well, we know that R gets mapped to P, the midpoints, W gets mapped to F, the altitude, and so on across. And the circumcircle gets mapped to a smaller circle. So what we end up discovering is that the midpoint of the sides and the feet of the altitudes all lie on a common circle. Let me go ahead and draw that in. And we can actually say something further when we consider the points A, B, and C. Whenever we take the homothency with respect to H on A, B, and C, we end up getting the midpoint of AH, BH, and CH. So the midpoints of these sides, these segments, all also lie on the circle. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 points on a common circle, and they have some importance with respect to the triangle. And this circle here is called the 9-point circle. And it's very useful inside geometry problems, as I will cover in a later video. But for now, let's go ahead and solve an Olympiad problem that uses the reflecting the orthocenter lemma. Suppose we have a triangle ABC and we let AD be the diameter of the circumcircle. And then there are points E and F that are on sides AB and AC, such that the circumcircle of AEF has tangents ED and FD. And we wish to prove that EF passes through H. So this is what it looks like in the diagram. Well, how can we prove this? We see the point H here. We want to find out what its relationship with EF is. And taking a closer look at it, it definitely appears that EH is equal to HF. So how could we prove this? If H is indeed the midpoint of EF, then we might be able to say that HD is perpendicular to EF. So that's something to consider. If we have this perpendicular line, then ABD is also 90 degrees. So we can actually try using phantom points here. Pretty much what phantom points are is that if we want to show that a point lies on a line or has some respect to a line, you let some H prime be the midpoint. Let's call it H prime. And we want to show that H prime is the orthocenter. So let's go ahead and draw HD and BD and CD. We have these perpendicular lines, so we immediately get off at the bat that EBDH prime and FCDH prime are cyclic. So that's something. We would somehow want to get rid of these tangent conditions, so we can say that angle DEF is equal to angle DFE, which ends up being angle EAF, which is just angle A, supposed to the triangle. So that's something to consider. We have that angle H prime ED is just equal to angle A, but at the same time it's equal to angle H prime BD. And we also have that angle HFD is equal to angle H prime CD. Since we know that these two angles are equal, we have that angle H prime BD is equal to angle H prime CD. But that's not necessarily enough, because we didn't really use this fact that it's equal to angle A. So what would have to happen if H prime was the orthocenter? We have these opposite angles are equal, so we might try to see if there's a parallelogram hidden. And that's where we end up striking the fact that BHCD is a parallelogram if H is the orthocenter. So because of what we proved earlier on in the video by reflecting the orthocenter. So if we can prove that BH prime CD is a parallelogram, we'd be set. We already have these two angles here, H prime BD and H prime CD, so we're kind of close. Well, now we can say that angle BDC, we're given that it's a diameter. So it's 180 minus angle A. So angle BDC is equal to 180 degrees minus angle A. But this angle here, as we proved given the cyclic quadrilaterals, is just equal to angle A. So this angle plus this angle here equals 180 degrees, implying that H prime B is parallel to CD. Similar logic implies that H prime C is parallel to BD, so H prime BDC is a parallelogram. That's what we wanted to prove, and this is actually enough to show that H is the midpoint of EF, since BHCD is a parallelogram where H is the orthocenter. Therefore, H equals H prime, and we're done. Actually, we can say even more about this. If M is the midpoint of EF, and AD is the intersection of the tangents, D is the intersection of the tangents at E and F, then angle EAM turned out to equal angle FAD. And they're both equal to 90 minus B. Now, why would this be the case? Well, we know that M must be the orthocenter here, so AM is perpendicular to BC, making angle BAM equal 90 minus B. On the other hand, angle CAD must equal 90 minus B because this angle here, angle ADC, must equal angle ABC by the cyclic quadrilaterals, which is angle B, and angle ACD is equal to 90 degrees from the diameter condition. So therefore, each of these angles is equal to 90 minus B. It turns out this is true for any general triangle. If we have a triangle X, Y, Z, and we construct a circumcircle, the tangents intersect at a point W, and we draw this line, and we have a midpoint M, then these two angles are equal. And this problem that we proved in the Olympiad can be used to prove this fact. Because we can construct a circle with diameter XW, and then where the midpoint is the orthocenter, we can take the midpoint of MW to get a point that's on the side BC, suppose. And then we have that XM must be perpendicular to BC. And given that, we can construct our triangle here, BC. And the rest proceeds as we proved in the problem. So in summary, we have that when we reflect the orthocenter across the side and across the midpoint, we end up getting points that are on the circumcircle of triangle ABC. This can be used to prove the existence of the 9-point circle, which is a circle containing the midpoints of the sides, the feet of the altitude, and the midpoint of the segments of AH, BH, and CH. And we use this fact to prove an Olympiad problem that relates to the concept of symmedians, which is what they're called. So thank you so much for watching. I hope you enjoyed watching.